Contents objective of our project, introduction, block diagram of energy meter, working principle of energy meter, block diagram, and working principle of the system, flow chart, circuit diagram, circuit description, simulation, Richland analysis, future work, conclusion and reference. And the next objective, remote monitoring of the energy meter, auto posting of data into server, removal of reluctant human involvement, remote power cutoff for non-payment of bill, in build data storage to maintain data integrity, remote cutoff of load from consumer side, use of easily available component with low cost. And
The next topic is introduction of energy meter. So energy meter is the most commonly used instrument in the field of electricity. Then primary object of our project is to design an electronic system which can attach with a conventional energy meter. The system will collect pulse from the energy meter and then calculate the pulse using some microcontroller and some web servers. The data is transmitted directly to a database server over an Wi-Fi communication. Next slide. Prasanto, next slide. Okay, now this is the block diagram of an energy meter. So working principle of energy meter now. So here in an energy meter, basically there are four important parts. The first one is that driving mechanism. Next one is that moving system. Third one is that braking system, and fourth one is the integrated system. So here, first one is that driving system. So here in the diagram, as we see here, two electromagnets. The first one is that of E shape. The next one is of C shape, and one is a braking magnet, and one is that pressure coil, which is also known as shunt coil, and another is series coil, which is also known as current coil. Now, this driving mechanism includes series coil and shunt coil. This coil is called shunt coil because this is parallelly connected to the supply. Now the number of turns in the shunt coil is generally very high, while the number of coils in the current coil is less. The conductor we use in the shunt conductor is also very thin, while in case of current conductor, the current coil, the conductor used is very thick. This is because if we see, we'll find out that in case of the shunt coil, the voltage supplied across the shunt coil is constant. So this means constant current will flow through that coil. That is why we are using only a thin conductors. But if we see in current coil, we'll find out that the current is directly coming from the load through this current coil. That is why we are using a thick conductor for the current coil. Now, in the next one is that mechanism, that is the moving system. How the system is moving. So when in the figure, if we see, we'll find out that first, when the current flow through the shunt coil, a flux will be generated in it, and due to this flux, immediately an eddy current will generate in the aluminum disc, which is present in middle of the energy meter as shown in figure. So now, if we see another part, then we'll see that the current is coming from the load through this current coil, and then there will also a flux generate, and due to this flux, again an eddy current will generate. Now we are assuming that the flux produced in the current shunt coil is phi p, while the flux generated in the series coil is phi s. Now then the eddy current is generated by the shunt coil will be ip, and similarly the eddy current generated by the series coil will be is. Now due to this ip current, that is the flux produced in the shunt coil, and due to the current component of this current coil, immediately a torque will generated in the disc. Similarly, due to the flux of this current coil and current components of this series coil of this shunt coil, again a torque will generate, and this resultant of these two torque will rotate our disc, which is the aluminum disc, at a particular speed. Now, this disc will rotate at high speed if the shunt coil is a completely inductive coil. I have already said that the number of turns in the inductor coil in the shunt coil is very high. This is the reason where we are using large number of coils in the shunt coil. And then for controlling mechanism, the next one is that braking of the system. That is, if the system is moving, then we have to control the speed of this rotating disc. How we will control, and it will control by a braking magnet, as we have seen in the diagram. So due to this braking magnet will also have its own flux. Then the flux already present in the aluminum disc will rotate, and so we'll again get a eddy current in the rotating disc. Due to this eddy current, again a torque will be generated. Now we know that according to Lenz's law, the response always opposes the cause. So here, new torque is generating only because of the original flux of this aluminum disc. That is why this torque will oppose the resultant torque we have already discussed, which is rotating the magnetic aluminum disc will oppose. And that is, it will try to control the speed of this aluminum disc. That is how the speed of this energy meter will be controlled. Now the last term is an integrating part. That means we are using some amount, consuming some amount of power. Suppose from the first day we are using some watt of power, some kilowatt, some amount of energy first day. Next second day we are using again some unit of energy, and then now this energy meter, there is a meter reading meter in above the energy meter, as we have seen in car through a arrow circuit, the green arrow signal, and this meter will accumulate all the energy consumed in the whole year or maybe in 1 month, and then it will display the total amount of unit consumed by us, and thus we can pay the bill according to it. Next slide. Next slide. Okay. And next slide. I have explained it. And the next one is that block diagram. This is the block diagram of our system. So the working principle of our system is not very complex. It is simple, very simple system. It is primarily based on pulse calculating and then capturing that unit and transfer it over in Wi-Fi. So the conventional energy meter generally available in market has an LED that keep flashing. The speed of this flushing depend on the amount of current consuming daytime. This count of pulse is varying from single phase to three phase. In case of single meter, there is approximate 800 pulses per unit. So if we can capture this pulse somehow from this indicator, then we can fetch this to the microcontroller we are using so that the microcontroller can count these pulses. So here we are using an optical communication, that is an LDR. As we can see, that is an optical sensor in our circuit. From energy meter to our device, to capture the light, the LDR is used. Depending on the light fall on the LDR, we know that the working principle of NDR, that is when an internal light fall on the LDR, internal resistance immediately change, that is drop. If the light falls on the LDR, internal resistance will drop and it will allow the current to pass through the next stage. That means now this output will move to the microcontroller, but this output is analog and the amount of this current, that is amplitude of this current, will be very low. That is why it is difficult for us to directly use it to the microcontroller. That is why we are using an amplifier, or that is operational amplifier, to amplitude this current signal. This amplifier will convert the analog input to some digital state, either it is higher or lower. We are using this op-amp in differential mode. Now, the output of this op-amp is connected to the microcontroller. We are using here 8089S52 microcontroller having 40 number of pins, and may operate between 4 volt, minimum 4 volt to maximum 5.5 volt according to datasheet. This program executing in the microcontroller will keep monitoring the pulses. Once we get reach 80 pulses, it will increase the unit by 1. That is, after 800 pulses, we will get 1 unit. And then again, it will reset to count the pulses back from 0. Now, whenever it increase the unit, that is, we are getting 1 unit, 2 unit, 3 unit, this unit information will immediately transfer to a Wi-Fi network, that is Wi-Fi module, and here we are using here ESP826601 Wi-Fi module. It is having 80 pin, and it is the smallest module of ESP8051, and it operates in generally 3.3 volt. Now, then this ESP module will configured with a router to connect with a server, and for demonstration we are using here mobile hotspot. Then from this Wi-Fi module we will send this to a web server. In between, the microcontroller, after getting the input from the microcontroller, will use an LCD to display the pulses, and an EEPROM to restore our memory electrically. That is how our system is working. Next step. Next slide. Okay, I have explained this. Next. Okay, this is the flow chart of our system. So if we see, we'll find out that first we'll start our system, then we'll initialize our LCD. After that, we'll display our introduction, and then we will initialize the Wi-Fi module as we have discussed, that is ESP8266, and it will display the pulse. Now, if it is true, then the device will stop. That is, it will reset. And after that, we'll read the pulses from the energy meter. And if we're getting pulses, that is, we'll get next pulse. That is, pulse is equal to pulse plus one. That is, first one single pulse, two pulse, three pulse, so four pulse, and so on. And if we does not get any pulse, then we'll display the previous pulse, that is 0, 0, 0. And after that, suppose we have displayed the pulse, then after 10 pulse, according to our monitoring and demonstration, that is generally for our project, it is 3200 pulses per unit. But for our for to make the system easy and for demonstration purpose, we are using 10 pulse equal to 1 unit. That is, if we are getting that pulse is equal to pulse per unit, after one pulse, we'll get the next 10 pulse, we'll get 1 unit. And after that, we'll get the next unit, that is unit is equal to unit plus 1. And after that, we'll display the unit and in the LCD, as we have previously said. Now, we'll write this unit to our EEPROM for memory to store this data. EEPROM. We know that EEPROM is used to store a small amount of data. And after that, we'll start the TCP, that is Transmission Control Protocol. That is, to any for any type of internet service to operate, it always needs some protocol. That is the protocol TCP protocol we are using here. And after that, we'll initialize the TCP and send data to the server, as I have discussed in the block diagram. And this is our system we are using here through the flow diagram. Sir, who is saying? Hello.
Good afternoon, everyone. Myself, Manas Jyoti Das. I am going to discuss about smart energy meter. Smart energy meter is an advanced metering technology involving placing intelligent meters to read, process, and feedback the data to customers. It measures energy consumption, remotely switches the supply to customers, and remotely controls the maximum electricity consumption. Smart metering system uses the advanced metering infrastructure system technology for better performance. They are capable of communicating in both directions. They can transmit the data to the utilities like energy consumption, parameter values, alarms, etc., and also can receive information from utilities such as automatic meter reading system, reconnect disconnect instruction, upgrading of meter, and other important messages. These meters reduce the need to visit while taking or reading monthly bill. Modems are used in this system to facilitate communication system and as telephone, wires, fiber cable, power line communications. Another advantage of smart metering is complete avoidance of tampering of energy meters, where there is scope of using power in illegal way. Prashant, next slide. Now, it is a very important topic, Internet of Things. Internet is by people, for the people, and about people. The internet is like a digital fabric that woven into the life of all of us. The internet is not just about connecting people, but also connecting things. Therefore, it is called Internet of Things or Internet of Everything. Let's take an example. We all have mobile phones. The mobile phones knows that how at what angle we are holding it or how much light in the room. So the next question arises, how Internet of Things will help us in our project. Internet of Things will help in reading the energy meter and send it to electrical servers, eliminating the need to visit a landman to take reading. And a very important point, we may set that day limit to our energy meter so that if we exceed our kilowatt hour consumption, a message will pop up in our phone, thus saving electricity. Next point, next slide. So web technology. Web technology refers to the means by which computers communicate with each other. Let's take an example. We all have mobile phones and nowadays the fitness band are popular. So the fitness band sends data to mobile phone, and we can track our performance with this technology. Prashant, next slide. So as discussed, data can be transmitted from one place to another through Wi-Fi communication. In our project, we have used a Wi-Fi regulated Wi-Fi communication, which operates on 3.3 volt. Thank you. Now I hand over my presentation to Prasanta.
Now I will explain the circuit diagram in our project. The circuit design for IoT-based energy meter is designed with easily available components. The heart of the system is designed with popular 8-bit microcontroller, that is 8089S52 from Atmel. To provide the power supply to the circuit, we are using a step-down transformer with the specification 220 volt primary and 12 volt secondary. The transformer is reducing the AC 220 volt into AC 12 volt. Hence, we must have to convert the AC into DC. For AC to DC converter, we are using a rectifier bridge designed with 41 and 4007 rectifier diode. The bridge will convert AC into DC, but there will be a noise or ripple. That is, we will get pulsating DC, which cannot be used for microcontroller-based circuit. Hence, a 1000 microfarad electrolytic capacitor is used as filter capacitor. Most of the components used in our circuit require plus 5 volt supply. Hence, we are using a plus 5 volt voltage regulator, that is 7805. The 7805 is having 3 pins. Pin number 1 is the input, while it can be give plus 5 volt to plus 18 volt, regulated or unregulated power supply. Pin number 2 is ground, and pin number 3 is regulated output. Irrespective of the input voltage at pin number 1, that is plus 5 volt to plus 18 volt, the output voltage at pin number 3 is always plus 5 volt. 7805 can provide at most 1 ampere current. To reduce any ripple or noise, two ceramic capacitors of value 100 nanofarad are connected from pin number 1 to ground as well as pin number 3 to ground as decoupling capacitors. The microcontroller we are using in our circuit is having 40 pins, where pin number 40 is VCC and pin number 20 is ground. According to datasheet, 8089S52 can operate from minimum 4 volt to maximum 5.5 volt. And typically, we are using 5 volt as the power supply. Hence, pin number 40 of the microcontroller is connected to pin number 3 of the 7805, and pin number 3 is connected to ground. But in Proteus module, pin number 20 and pin number 40 of the microcontroller are not displayed. Any microprocessor or microcontroller require clock pulses to fetch instruction and execution. Few microcontroller has internal oscillator circuit like ATmega 8, ATmega 328, etc. But 8089S52 is not having internal oscillator. Hence, we must have to use external clock source. To provide, we can use different clock source like crystal oscillator, resonator, time circuit, etc. But in our circuit, we are using a crystal oscillator of value 11.0592 MHz. Pin number 18 and 19 of 88NS52 are XTAL2 and XTAL1 respectively, where we have to connect the crystal oscillator. According to datasheet of 88NS52, can operate up to 33 MHz, but we are using 11.0592 MHz as the microcontroller which will communicate with the Wi-Fi modem through serial communication. In case of serial communication, we must have to use 11.0592 MHz for error-free in data transfer and reception. From pin number 18 and 19, we have to connect two ceramic capacitors of value 33 picofarad to ground. According to the data sheet, this C1 and C2 could be anything in between 20 picofarad to 40 picofarad. We have chosen 33 picofarad as it is easily available. Pin number 9 of 88NS52 is reset pin. According to datasheet, we have to provide high at pin number 9 for 2 machine cycles. The device will restart and for normal operation, pin number 9 must be pulled down. Hence, a 10K resistance is connected from pin number 9 to ground as pull down. To create the reset circuit, we are using a push to on momentarily tactile switch between pin number 9 and VCC as shown in the circuit. Pin number 31 of the 88-52 is external axis. If we have to use the external memory, pin number 31 must be connected to ground. And to use the internal memory of the microcontroller, pin number 31 must be pulled up or connected to VCC. 88S52 is having 8K of flash memory and 256 byte of RAM. As we are using the internal memory, the microcontroller pin number 31 is connected to VCC in our circuit. To display the relative information, that is number of unit pulse or status of the connectivity, etc., we are using a 16:2 LCD in our circuit. The LCD module is having 16 pins. Pin number 1, 2, and 3 are ground, VCC, and contrast control. Pin number 1 is connected to the ground, pin number 2 is connected to the VCC, and pin number 3 we have connected a potentiometer to adjust the contrast of the LCD. Pin number 4, 5, and 6 are RS, RW, and EN of the LCD respectively. The RS pin is used to specify the resistor selector. At the time of sending command to the LCD from the microcontroller, RS pin must be pulled down. On the other hand, at the time of sending data from the microcontroller to the LCD, RS pin must be pulled up. The RW pin is used to specify read or write mode. At the time of writing data or command from the microcontroller to the LCD, RW pin must be pulled down. On the other hand, at the time of reading acknowledgement or busy bit from the LCD, RW pin must be pulled up. The EN pin is used to provide a high to low pulse during or after providing data or command from the microcontroller to the LCD. In our circuit, the RS, RW, and EMP are connected to pin number 39, 38, and 37 of the microcontroller, that is port 0.0, port 0.1, and port 0.2. The microcontroller 8852 is having 4 I/O ports, that is port 0, port 1, port 2, and port 3. The internal pull-up of P1 and P2 are activated, but the internal pull-up of port 0 is not activated. Hence, we must have to use external pull-up. If any I/O pin of port 0 is used in circuit, then external pull-up must be added. As we are using port 0.1, 0.0, and 0.2 to provide RS, RW, and EN signal of the LCD, three 10K resistance, that is R2, R3, and R4, are connected from plus 5 volt to the I/O pin as pulled up. Port 0 of 88-52 is open grid. Pin number 7 to pin number 14 of the LCD module are data command bus. Through this bus, microcontroller need to transfer data or command to the LCD. In the circuit, port 1 of 88-52 is used to provide data or command to the LCD. Hence, pin number 1 to pin number 8 of the microcontroller is connected to pin number 7 to pin number 14 of the LCD module, as shown in the circuit. In our project concept, the microcontroller need to get the pulse from the energy meter. To get the pulse, either we can use a wire to connect from the pulse output to the microcontroller I/O pin, but it is not safe. To protect the circuit from spike and electrical noise, we are using an optical signal to get the pulse. If we use optical connecting between the energy meter and the microcontroller unit, it will not only prevent from circuit damage as well as it will not violate or tamper the energy meter. To get the pulse from the energy meter, a LDR is used as optical sensor. The resistance of LDR change depends on the light fall on the LDR. In the circuit, the LDR is placed as a port of voltage divider circuit. According to the voltage divider rule, when a 10K resistance is used as R1 and the LDR is used as R2, as V input is plus 5 volt using the circuit, according to this arrangement, If light fall on the LDR, the Vout will drop. The output of the voltage divider circuit is fed to time non-inverting input of the comparator. If we using an op-amp in differential mode as threshold value, that is at inverting input, a voltage level is set with the help of a potentiometer. By rotating the potentiometer, we can set the threshold value at a particular level. When the non-inverting input drop below the threshold value at inverting input, the non-inverting input will go low. Otherwise, the output will be high state. We have designed the circuit such a way that when light fall on the LDR, the comparator give a low pulse to microcontroller IO pin. The program executing in the microcontroller is responsible for monitoring the status of the IO pin, where the sensor output is connected. When the IO pin goes low, it increments the counter by 1. And according to the manufacturer of the energy meter, 32,000 pulses equal to 1 unit. And it is count 30,000 pulses, it will increase on another memory variable unit by 1. For experimental purpose, we have taken 10 pulses equal to 1 unit. After getting a new pulse and the calculated unit, the microcontroller is sending data to the LCD to display the current state. So now we have connected a EEPROM in the port 2 of the microcontroller. So the EEPROM is having 6 pins, that is SDA, SCL, WP, A0, A1 and A2. So SDA and SCL is connected to the port 2.0 and 2.1 of the microcontroller. As SDA and SCL are open range, so we must have to pull up to communicate with the EEPROM. So two pulled up registers is connected in between VCC and the EEPROM. And the Wi-Fi module we are using is ESP8266, which having 8 pins. And one is having 8 pins. The transmit pin is connected to the receive pin of the microcontroller, and the receive pin is connected to the transmit pin of the microcontroller. And the ground pin is grounded, and the VCC is connected to the 3.3 volt supply. As it operates only in 3.3 volt supply, so we have to use a voltage regulator of 3.3 volt output. So we are using S11733 as a voltage regulator, which gives 3.3 volt output. And the pin number 2 is the chip select, which must be pulled up to operate with it. So we have connected a resistance with the VCC to pull up the pin. And as a circuit breaker, we are using a relay as shown in the bottom of the corner. So the relay operates with the two transistors as the switch. The microcontroller is not the microcontroller is not giving the high pulse to get the switch open. So we have to pull up the transistor as we have shown in the circuit.
We have taken 10 faults equal to 1 unit in our program, and it is displaying both faults and unit. The system is successfully storing the unit value in the EEPROM. When we start the unit, it is reading the last unit from EEPROM and continue from that unit. Next slide. And this future work. It can be introduced in the Department of Power and Energy and can be sanctioned for the collection of details of the consumption unit for each and every customer. Further, it can be linked with any payment gateway so that The electricity bill be payment can be also be done online with it.
General, EPROM stands for?
Yeah, yes, ma'am.
EPROM stands for?
EEPROM transform.
Stands
Electrically
for?
programmable read only memory.
Okay. So what is the bandwidth of an idle op-amp?
What, ma'am?
Bandwidth of an idle op-amp?
Bandwidth or idle pump?
Yes.
Don't understand, ma'am.
You're not getting my point. What is the bandwidth?
Oh, yeah. Bandwidth.
Oh, sir. Okay, sir.
Okay.
So our objective was to capture the pulse from the energy meter, hence fetch it to the microcontroller to count the unit and transmit it over Wi-Fi communication to the web server, where the server-side program and store it in the database server.
Hello, Prashant, have you completed your conclusion, or you have something else to say?
Sir, last is the conclusion and the reference is there.
Okay, no problem. We can read it. Okay, so uh, I have a question for you. Okay, I have a question for all of you. That means the whole group. So you were working on
Okay,
energy
sir.
meters, right?
Yes,
Hello,
sir.
I need a feedback from students. Can you hear me?
Yes, sir.
Yeah, Prashant can hear me. Other people?
Yes, sir.
Yes, sir.
Okay, Chandra can hear me.
Manas also.
Manas can hear me.
Yes,
Okay,
sir.
very good. So you are working on energy meter, right? So energy meter,
Yes,
you
sir.
are installing it domestically or in industries, right? So let us talk of domestic energy meter. Okay.
Okay, sir. Okay, sir.
Okay. So
Okay,
in
sir.
domestic, you are having some RL load. The load in our house is RL type, resistive inductive type.
Yes,
Okay.
sir.
Right. So suppose you are getting a value in your energy meter that this much amount of energy has been consumed
Yes, sir.
for a certain for your house, and after 2 days you have increased the inductive part.
Hmm.
Are you getting my point? You have
Excuse me,
increased the
sir.
induct. Hello.
Hello, sir. Sir, please can you explain it again?
You are working on energy meter. Energy
Yes, sir.
meter measures energy. So in your house, you are having RL type of load, RL type of load. Till here, it is okay. Hello, hello. Can you hear me?
Yes,
Yes,
sir.
sir.
So in your house, you are having RL type of load. So suppose you are
Yes, sir.
using, suppose you are increasing that L part, not that
Okay.
R part.
Okay,
You
sir.
have increased the inductive load of your house. So your
Okay.
energy meter will show a difference, right?
Yes, sir.
Will it show some difference or will it not show some difference?
Sir, it will show some difference, obviously.
Okay, it will show some difference. Is it?
Yeah. Yes, sir.
Uh, Prashant, is she telling correct? So what difference it will show?
Sir, after increasing the inductive load,
Hmm.
the aluminum discs we are using to measure the power consumed, it will deflect at a higher speed. So we'll get a large amount of units because it will, if the speed increase, that means the unit is also increased because unit is related to the total amount of energy you are consuming. That is power consuming per unit hour. So if it deflect at higher speed, then it will definitely affect the unit of the unit we are consuming in our energy meter.
Okay, so can you tell me what is the unit of your unit?
Yeah,
What is
it is kilowatt per hour.
Kilowatt
No,
per hour,
sorry,
sir.
sorry, kilowatt hour.
kilowatt hour, right?
Yes,
Yes,
sir.
sir.
Okay, and in kilowatt,
Yes.
is there any reflection of inductive load or capacitive load?
Sorry, sir.
In that kilowatt, you have heard of three type. You have heard of three type of power, right?
Yes.
Watt,
Sir.
VA,
Yes.
and VAR,
Yes, sir. Yes.
right? So
Yes,
in
sir.
this kilowatt, is there
Yes.
any reflection of inductive and capacitive load?
Inductive and capacitive loads. Obviously, sir. It will.
Yes, sir.
Yes, sir.
Is it?
Yes.
Yes, sir.
Okay, you try with the diagram that you have learnt in first year or second year. That watt VA and VAR. You see
Yes,
that
sir.
what happens there?
Okay, sir.
Okay, okay, thank you.
Thank you, sir.
Okay, I will ask a basic question. Okay.
Yes.
So what's the difference between indicating, recording, and
Hello,
integrating instrument?
ma'am. If now if meeting will be ended, I will start it again. You will ask questions. Okay, you carry on.
Okay, sir. Okay, sir. So, what is the difference between indicating, recording, and integrating instrument?
Hello, ma'am.
Yes, next, sir. Oh, yes. What is indicating instrument? Indicating, recording, and integrating instrument. Difference between these three.
Hello, ma'am.
Yes, Manas.
Ma'am, as in energy meter, a light glows 5 times and then it stops for 1 second. That is indicating.
Indicating.
Say about integrating device, integrating instrument, then suppose we are having this energy meter. Energy meter has a very important part that is nothing but integrating type. That is, suppose in the first day I am using 1 unit, consuming 1 unit energy, and the next day we are using 3 unit, 4 unit. Like this, the energy meter will integrate. That is, it's accumulate all the energy we are assuming in the whole month, and then it will show us the total limit after 1 month. That is the integrating part. It is this type of device is called integrating device. Or the last one is, ma'am, Arvata ki asile? Indicating
Recording.
recording. Sorry. Recording means it will like we are using here ESP8266. It is our Wi-Fi module. This module will always store our total amount of
Total amount of what? Yes, Nandita.
Nandita. Hello, Nandita.
Hello, ma'am.
yes,
Okay.
sir.
Yes, Nandita.
Yes, yes, ma'am.
Okay, what is it stored?
It store the pulses or it may store the data. If we say about we are using here EEPROM, so it will store the data in binary form because we are here you are using serial communication, so the data will be stored in binary form in our EEPROM or Wi-Fi module also.
Okay. Okay. General Pegu. General Pegu.
Yes,
If
ma'am.
the supply voltage of energy meter is more than the rated value, okay, then
Yes.
your energy meter will run fast or slow.
I think
Okay, listen. If
yes.
the voltage supply to the energy meter is more than the rated value, then the energy meter will run fast or slow.
More than then it become fast, ma'am.
It become fast.
Yes,
Why?
because the voltage is more.
I don't think so. Prashanta,
Yes, ma'am.
Prashanta?
Yes, ma'am.
Okay, what happened when voltage supply of energy meter is more than the rated value?
Ma'am, the energy meter speed is depend on the load only.
Load only.
If load is increased, then the energy meter will run fast. When the blinking
So
of the
according to you, so
LED
Prashanta,
will
according to you, if the voltage supply of energy meter is more than the rated, it won't affect the performance of energy meter. Manas,
Hello, ma'am.
yes, Manas.
Yes, ma'am.
So are you agree with Prashanta?
Ma'am, just now I came, ma'am.
Oh, okay, okay. I repeat my question.
Okay,
Okay,
ma'am.
Manas, if the voltage supply to the energy meter is more than the rated value, then the EM will, your energy meter will run fast or slow.
Ma'am, pardon, please.
If the voltage supply, okay,
Yes,
voltage we supply to the energy meter is more than the rated value, then the
yes, ma'am.
energy meter will run fast or slow.
Ma'am, it will run constant, ma'am.
It will run constant.
Yes.
Ma'am, I think it will run slower.
It will run slower.
Hello, ma'am.
Yes,
Why
Nandita.
it will run faster, Prashant? It will run in constant speed.
Yes, sir.
What you told? You told it will run faster or it will run in constant speed.
I think so. It will run slower if the rated value.
Why it will run slower?
Hello.
Yes, Nandita.
Hello, ma'am. I think when if the rated value change, then this will affect the system stability because we know that rated voltage means balanced voltage. We are assuming. So if we are using three-phase voltage, that means if the rated value change, then obviously it will affect the stability of the whole system. Then I think it will may slow down or unstabilize the system.
Oh, no. You see that it will change the stability till here it is correct. But
Yes,
it
sir.
will slow down or it will make it fast. That is the question.
Okay, sir.
So that you have to answer that it will be fast, it will be same, or it will slow down.
Sir, slow down.
Slow down, sir.
Okay, tell it to ma'am, and I want to hear the logic. Why it will slow down?
Okay, sir. Hello, ma'am.
Yes, it is slow, but what is the logic behind it?
Ma'am, is this voltage we are supplying in the sun coil is a rated voltage. We have assumed it previously, and according to that, our energy meter is showing out some readings. So if the voltage rated voltage changes, then if the voltage change, then the inductance, the coil which is present in the sun coil,
Mm.
it's now will have less inductive effect. So if the inductive effect is less, then it will obviously affect the flux, and then flux affected. That means it will affect our eddy current, and if the eddy current is affecting, getting less amount of eddy current, that means torque will also less. And if the torque is less, then the motion of this aluminum disc, which is present, which is giving us some readings by moving it, the speed of the disc will decrease. So if the speed decrease, that means it will moving slowly than the original rate. That is why after rated voltage, it will slow down.
Hello, ma'am.
Yes, yes.
Can you explain this in simple way with Ohm's law?
Okay, you can try.
Okay, ma'am. As we know, V equals to IR.
Yes.
If voltage decreases, so current also decreases. And as we all know, energy meter measures power. That is P equal to I square R. If current is less, the reading will be less, ma'am.
No.
current is less, your reading will be less.
Yes, ma'am. In meter, the reading will be less because we are consuming
No,
more power.
Mm,
but I think that's the eddy current, right?
mm.
Ma'am, am I
The
right?
current.
Okay, you just confirm the logic behind it. Okay, my next question is, okay, in a shading band, yes, Nandita, you just right now you explain about the shading bands, right? So
Ma'am, sorry, can you say it
shading
again?
band, shading bands,
Band.
yes, bands,
Okay, band.
shading bands.
Okay,
Okay, so
okay.
the adjustment of in shading band, adjustment of position is done. So why
Sorry, sorry, ma'am. It is not clear.
it's not clear?
Ma'am, can you say it again?
Yes, Nandita, in shading band, okay, adjustment of position is done. Why?
Ma'am, sorry, but your question is not clearly audible.
I'm not audible. Now you can hear me, Nandita?
Yes, ma'am. Yes, ma'am. Now it's clear.
Okay. Nandita, okay, this is for all of you. Okay, question is for all
Yes.
of you. Okay,
Okay,
in
ma'am.
Okay, ma'am.
setting bands, adjustment of position is done. Why?
Ma'am, which band, ma'am?
Shading band, shading band.
Okay, okay, okay. Setting band. Yes. Okay, ma'am.
Yes,
Yes.
adjustment of position is done. Why?
Ma'am, due to the phase angle.
Due to the phase angle.
Yes, ma'am.
No.